Hi everyone, how's it going? I hope you're doing well. My name is Professor Andrew Timming, and I want to extend a warm welcome to you. Welcome to Chapter 7, Lecture 1. This lecture will correspond to Chapter 7 in the textbook Applied Statistics, Business and Management Research. And I just wanted to point out that we are halfway through the textbook. That is to say, we're halfway through this course. So congratulations, you've gone through 6 chapters learning about data science and applied statistics, and we have another 6 chapters left till we reach the end of this course. We're still looking at bivariate statistical tests at the moment. You'll recall that in chapter 5 we looked at the t-test, the independent samples t-test. In chapter 6 we looked at the ANOVA, the one-way analysis of variance. Both of these are bivariate statistical tests. And in this chapter, we'll be looking at the ChiSquare test. Yes, I know it looks like it should be pronounced chi, like the T, ChiSquare, but it's not. It's pronounced chi. So we'll be looking at the ChiSquare test, which is also a bivariate statistical test. That is to say that it involves one independent variable x and one dependent variable y. But unlike the t-test and unlike the analysis of variance test, this is a non-parametric statistical test. Don't worry too much if you don't understand what that word means, because I will explain it in this lecture. Okay, let's do it. Here you can see the textbook that we're using in this lecture series. It's called Applied Statistics, Business and Management Research, and it was written by yours truly. I hope you have enjoyed reading it. I hope you'll continue to enjoy reading it, and you're welcome to purchase a copy of it. It's available at most major bookstores, or you can order it online as well. But should you not want to purchase a copy of it, that's absolutely fine by me. You're welcome to visit your local library, particularly a university library is likely to have a copy of this book, and if it doesn't, you can certainly request that they get a copy of this book. Okay, so let's jump right in, starting with Chapter 7 on the chi-square test. So how about we start with the most fundamental question, which is, what is a chi-square test? What can we use it for? How, in particular, does it differ from the previous 2 statistical tests, bivariate statistical tests, that we've learned about so far in the last 2 chapters of this book? So as I said in the opening of this lecture, what differentiates the chi-square test from the previous 2 tests, from the t-test and the ANOVA, is that the chi-square test is what we refer to as a non-parametric statistical test. All right, so it's a non-parametric statistical test. And this test compares observed results, that is to say that we can see and we can observe, with expected results. So these are results that we might expect between 2 variables. And the 2 variables that we use in a chi-square test, that is to say x and y, have to be categorical variables. That is to say they have to be either nominal variables or ordinal variables with a few categories. Say, for example, no more than 4 categories, because in theory you can do a chi-square test with, say, for example, nominal or ordinal variables with more than 4 categories, 5, 6, 7, 8, if you have a large data set. But the results are quite difficult to interpret when you have a lot of categories. So keeping the number of categories or the number of groups to a minimum is ideal. Okay, so what do we mean by a non-parametric statistical test? So you'll recall that when we learned about the t-test and the ANOVA, these were described as parametric tests. And what I mean by parametric tests is that they are predicated on the normal distribution, right? The bell curve. And you'll recall that the dependent variable in both t-tests and ANOVAs has to be either ordinal or preferably scale level. And the reason is that when we make that generalization, that quantum leap from the sample to the population, we do that based on a mechanism uh, based on our knowledge of the geography of the normal distribution. Now, the chi-square test is not predicated on normality. That's why it is called a non-parametric test. The chi-square test doesn't depend on a normal distribution, and that should make sense. It makes sense in the sense that if you're looking at two nominal variables and how they're related to each other, well, nominal variables by definition cannot be normally distributed. They don't produce a bell curve naturally because they're nominal, they're non-hierarchical. So what we do when we calculate a chi-square test is we usually employ what we refer to as a contingency table. So a contingency table is a table that consists of rows and columns. These are our independent and dependent variables respectively. And at the intersection of each category across the independent and dependent variables, we have cells that tell us about the unique intersection at that particular place. And what we do is we assess whether or not X is associated with Y, or whether X is dependent on Y. And if it is, then that will be reflected in the p-value, which we can look at a little bit more closely. Okay, so when you learned about the t-test, the independent samples t-test, what we did was we went through an example of how to calculate a t-statistic, right? So you remember the formula for calculating the t-statistic that compares two mean scores across two groups. And that t-statistic tells us something about the magnitude or the difference between those mean scores. And you'll recall that that t-statistic has a corresponding p-value, and that p-value tells us whether or not we can generalize the results of our t-test. The same is true of the ANOVA test, which we looked at in the previous chapter, right? So the ANOVA test looks at mean scores across 3 or more groups in our independent variable. And what we do with an ANOVA test is we calculate something called an F statistic. And that F statistic tells us something about the magnitude of the differences across the mean scores in our independent variable. And if that F statistic is large enough, it will have a corresponding p-value that may suggest statistical significance. The same is true with a chi-square test, except in this case, we calculate a chi-square statistic, and that chi-square statistic tells us something about the strength of the relationship between x and y. And the larger the chi-square statistic, we can conclude the greater the dependence between those two variables, x and y. And as with the t-test and the ANOVA, we calculate a chi-square statistic that is accompanied by a p-value. And if that p-value is less than 0.05, which is the commonly agreed upon cutoff that we as data scientists use, then we can assume that the two variables are statistically significantly related to one another, and therefore that the result, the association between x and y in our sample, generalizes to the broader population. Okay, so let's look at the types of research questions that we as data scientists can ask and answer using a chi-square test. Now, some of these research questions might appear a bit silly and non-realistic, but I think they're useful for purposes of showing you the types of questions and the types of configurations of variables that are involved in a chi-square test. So let's take them one by one. First question on this slide: are people who drive Audis greater risk takers than people who do not drive Audis? I ask this question because, when I drive out on the highway, I always seem to be passed by people driving Audis? I know it's a bit of a generalization, but it's a research question. We don't know the answer, so that's why we're trying to find out. Maybe I have a suspicion that people who drive Audis might be greater risk takers than people who don't drive Audis. So in this case, the independent variable is, do you drive an Audi? Yes or no. That's a nominal variable. And are you a risk taker? Again, you could ask that as yes or no. So we've got two nominal variables, and we're looking at whether there's this association between them. Are people who use psychedelic drugs more creative than people who do not use psychedelic drugs? So maybe there's an association between this type of drug use and creativity. So our independent variable is the psychedelic drug use. Do you use psychedelic drugs? Yes or no. And the dependent variable is a nominal measure of creativity. So how creative are you? Very creative or not very creative? Or you could ask, are you creative? Yes or no, depending on how you want to measure it. Are people who work overnight shifts more likely to have an accident at work than people who work day shifts? So maybe you assume that there's potentially an association between shift work and having an accident. So our independent variable here is whether you work day shift or overnight shift, and our dependent variable, our outcome, is whether you've had an accident in the last year. So you could measure that by do you work day shifts or night shifts, and have you had an accident at work in the last year, yes or no? Are people on Twitter less productive than people who are not on Twitter? Right? So this is potentially an interesting research question. Maybe you assume that if you're on Twitter, you're probably checking your Twitter account all day long and therefore not engaging in work. So your independent variable here is, are you on Twitter? Yes or no. And your dependent variable is some measure of productivity. I am not productive, or I'm in the top 50th percentile of productivity, or I'm in the bottom 50th percentile of productivity. Again, depending on how you want to measure it. Are alcoholics more likely to have been involved in employee misconduct than non-alcoholics? Right? So this seems like a sensible question. You could ask this question, is this person an alcoholic? Yes or no? And has this person been involved in employee misconduct in the last year? Yes or no? All right, let's look at a few more research questions. Are data scientists more likely to be employed than non-data scientists? Right. So our independent variable is, are you a data scientist? Yes or no. And our dependent variable, are you employed? Yes or no. Are politicians more likely to lie than non-politicians? So our independent variable is, are you a politician? Yes or no. And our dependent variable is, are you more likely, or is this person more likely to lie? Yes or no. Are women more likely to have experienced sexual harassment at work than men? Our independent variable in this case is gender, let's say male and female, and our dependent variable is, have you experienced sexual harassment? Let's spend a little bit of time looking at our next variable, or our next research question, excuse me. Are psychology majors better at dealing with people than engineering majors? So let's take a look at that one in a bit more depth. Are psychology majors better at dealing with people than engineering majors? This seems a reasonable research question to ask, and just think on your own for a minute or two about what you might expect, or whether you might expect there to be a statistically significant association between these two variables. So let's first start by asking, what's our independent variable and what is our dependent variable in this chi-square test? The independent variable in this case would be your major. So are you a psychology major or an engineering major? And our dependent variable would be dealing some measure of the effectiveness with which you deal with people. So do you consider yourself a good people person? Yes or no? So that just gave you an example of how you'd measure those two variables. You measure your independent variable by simply asking, are you a psychology major or an engineering major? And you'd measure your dependent variable by asking, do you consider yourself a people person? Yes or no? So how big of a sample will you need? Again, as with any other statistical test, the larger the sample, the better off you are. You're going to want to have at least a couple hundred if you're doing a chi-square test. If you have a couple thousand, that would be ideal, that would be great, but at least a couple hundred. And the reason is that you want to make sure, if you're thinking about this association in terms of a contingency table and you're looking at the intersection of the different categories, you want to make sure as a rule of thumb that each cell within your contingency table has a minimum of 5 respondents, right? So if you have less than 5 respondents, it's going to be difficult to calculate your t-statistic in any meaningful way. So what kind of result might you expect here? My guess is you're going to find that psychology majors are indeed better at dealing with people than engineering majors. And how could you use this research to improve management decision making? Well, clearly, if you're hiring for a role that involves a lot of dealing with people, it might make more sense to look for psychology majors as opposed to engineering majors. Okay, every statistical test has a set of assumptions that we should seek to achieve or seek to meet before we carry it out. These are some of the assumptions associated with the chi-square test. First of all, I would point out that, as I've said earlier, normality or a normal distribution is not an assumption of the chi-square test. The chi-square test is a non-parametric test, not a parametric test. Therefore, the concept of the bell curve of the normal distribution is irrelevant in the context of a chi-square test. But as with the other statistical tests that we've looked at so far in this class, it's important that the sample is randomly drawn. And the reason is that randomly drawn samples tend to look and behave more like the population than non-randomly drawn samples, which tend to be more biased. Your independent variable in the context of a chi-square test has to be either nominal or ordinal with at least 2 categories, right? So you have to have a minimum of 2 categories. But as I said before, you don't want to have a lot of categories either, because then the interpretation of the chi-square test gets quite difficult to identify patterns in the data. Similarly, your dependent variable must also be categorical. That is to say, it must be nominal or ordinal. And it too must also have at least 2 categories, but not a lot of categories. And the final assumption of the chi-square test is that each observation in your sample has to be independent of every other observation for the results of your chi-square test to be meaningful. Okay, so that gives you a brief and hopefully succinct introduction to the chi-square test. Hopefully you understand what the chi-square test is and what types of research questions that we might ask and crucially answer using a chi-square test. Now that you have this foundation of knowledge around this chi-square test, you can move on to Chapter 7, Lecture 2, where we will look at how to calculate a chi-square test. So we'll go through an example of how you mathematically calculate the chi-square statistic, and then we'll look at how you would interpret the results of a chi-square test and how you would do it crucially on SPSS. So thank you very much for listening, and I bid you adieu. Bye now.